Okay, so we're going to look at how do you model exponential growth and decay problems. Okay, this is the second part of sections 7.1 and 7.2. So the formulas are here for exponential growth, exponential decay. The difference is we're going to add the rate versus subtracting the rate for decay. Okay, so A is my initial value, initial amount, R is my rate, T is my time. Okay, so for example, let's just say I have $100 and I want to put that into an account that gains 10% interest. Okay, 10% as a rate would be 0.10 as a percent. So that means my growth factor, which is 1 plus the rate, which would be 1.1, is what I would use as my base. T is the time, so let's just say after 1 year. Well, I just multiply 100 times 1.1 and that's $110. Okay, so that makes sense. Okay, after 2 years, I would raise 1.1 to the 2 and then multiply that by 100. Okay, so that's how we do these kind of problems. So let's look at the first one here. 1992, there were 2,000 rabbits. Population increases at 12%. How many rabbits will there be in 2014? Okay, so there's 2,000 rabbits. That's my initial amount. My rate is 12%, so that's 0.12. And raise it to the number of years from 92 to 2014. So that would be, I believe, 22 years. Okay, so now I'll just add that together and I get 1.12. And I go to my calculator, and my calculator is giving me 24,200. And I'll round it up to 24,201 because we can't have a fraction of a rabbit. Okay. Number 2, exponential decay because the value is decreasing at 7% per year. So let's say I purchase a snowmobile for $4,000. What's it going to be worth in 5 years if it decreases at 7%? Okay, so let's see how I set that one up. Initial value is 4,000. 1 minus the percent. 0.07 is 7%. Raise it to the 5 power. That would be 0.93. So 0.93 to the 5. So this is, just show this on the calculator how you would enter that in. 4,000 times 0.93 in parentheses raised to the 5th power. Hit enter there, and I get 2782.8. 0.75 actually. So your snowmobile is now only worth $2,782.75. Okay, another one. Now we know the value decreases at 12% per year. We want to know after 5 years it's now worth $2,000. So what was the original cost? Okay, so now we're solving for the A, and we know the future cost. So we're going to set this up. To the 5. It's going to look like that. So now what I need to do is figure out what 0.88 to the 5 is. Which is 0.5277. Divide by that over on the other side. And I get 3790. So it was worth about $3,790 5 years ago. Okay. The other thing in this section, compound interest. Okay. So when you put money in a bank, you can have interest compound not necessarily annually, but you could have interest compound quarterly, which would be 4 times a year, or you could have it compound monthly. So what that means is, let's say I have a 12% annual interest rate, and I have it compounding monthly, then my interest compounds every month. It compounds 1%, because 12% divided by 12 months would be 1% per year. Okay, so there's advantages. The more it compounds, the more interest you gain, and the more money you'll have in your account. Okay, so let's look at the first one. I invest $8,000 in an account at 6% compounded quarterly. Quarterly means 4 times a year. What's the balance after 4 years? Here's my equation. Okay, so A is my future amount, P is my principal, which is the initial amount, R is my annual interest rate, N is the number of times per year it's compounded. And then there's N times T. So the exponent here needs to be how many times my interest is compounded over the number of years. So if I put money in the bank for 10 years and it's compounded quarterly, there will be 40 times that the interest is compounded. And the rate divided by the 4 for quarterly would tell me the rate per quarter. Okay, so on this one, I'm going to have $8,000. My rate is 6%, that's 0.06, divided by N, which is quarterly, which is 4, and then 4 times 4, because it's quarterly is 4, and for 4 years. So there's my equation. And now I just plug it into my calculator. So let's just simplify it down first. So this would be 1.015 to the 16. It's going to give me 10,151.88. So after 4 years, that's what I'd have in my account. Okay, one more. You don't see many bank accounts that compound interest daily, but let's just do this example and see. Oops, not 8,000 anymore, it's 2,000. So I'm putting 2,000 in my account. My rate is 4%, which is 0.04. Daily, so there's 365 days in a year, so that's what my N is. And we got 365 times 3, because it's 3 years. So that's what my equation would look like. So on my calculator, I get this, 1.09 E minus 4. That's scientific notation. So that means that I need to move that decimal spot 3 spots to the left. So I'm actually getting, when I add 1 to it, I'm getting 1.0001096. So try to keep as many decimal places as you can. It's actually 9. I'll even move it over 9589. So if I went on my calculator and I hit +1, and so that's my growth rate. Now I'm going to raise that, and I'm going to put parentheses there, and I'm going to take 365 times 3 years. And that's going to raise that number to the power, which is the 1.12. So that's so what I've done is I've taken this and raised it to this power in parentheses. Now I'm going to multiply it by 2,000. And I'm going to get 2,254.98. Okay, so after 3 years compounding daily, I went from 2,000 to 2254.98. Okay, so that is how we do exponential growth and decay problems and compound interest problems.